Okay. So I'll give a few more minutes for folks to come in. While I'm doing that, I'll put that camera set up here. There's the 16th of September. And what we're going to do today, we're going to finish section 7.2, sorry. So I mentioned that there is a similar strategy for secant tangent integrals as for the sine cosine integrals. We're going to be talking about integrals of the form some power of secant times some other power of tangent. And the reason we do this, we break this section down into powers of secant times powers of tangent and powers of sine times powers of cosine, is because any mess of trig functions can be rewritten that way if you're patient and clever. You may end up using cosecant, cotangent sometimes, but the rules for those are the same as the rules for these. I want to warn you that there is a nightmare case here. It's possible that these integrals can just be healthscapes. In the healthscape case, I will show you how to do one or two problems, but with my last class, I got roped into trying one that I couldn't do. It could be done, but there was just nowhere near enough time. So these problems can very quickly get out of hand if you're not careful. But the trick is to be able to recognize whether this is one of the easy guys or one of the hard guys. So I'm going to show you how to do that. The three cases we're going to consider . So just like the sine cosine integrals, we considered two cases, right? Where one of the powers is odd or neither power is odd. Here, the three cases are going to be the power of secant is even. And in these, we're going to want to try to sub for tangent. We'll consider the case where the power of tangent is odd. And in these, we're going to try to sub for secant. And then the case outside of these is the case where the power of secant is odd. And the power of tangent is even. And these, we're going to use some IVP in the loop, and they're hard. There's a question in chat asking when the test is going to be. That's a fair question. So let's take a look at your syllabus. You guys are in section 2, but it's the same syllabus. So just slightly different dates. Right now we're here. And we wanted to be here last week. So today I'm going to finish the trig integral stuff. And then Friday I'm going to introduce trig sub. Next week, you're going to have trig sub, partial fractions, and summary problems. So the exam, it would not be fair for me to give you the exam next week. I like you to have a full week with the study guide, which means that probably the exam is going to be not next week, but the start of the following week. So I would expect exam 1 to be somewhere around 9/28. Now, I'll give you the exact date once we finish section 7.4 on partial fractions. It depends on how long it takes us to get here. As soon as we finish 7.4 on partial fractions, I will release the exam 1 study guide. And from that day, you will have precisely 1 week before the test. Okay? So that's the plan. Before we get into these, are there any homework problems you guys want to take a look at? Anything that's been driving you nuts?
Can we go over number 3? I think it was. I got it right, but I was getting stuck somewhere, like a lot.
Sure. So it's cos squared from 0 to pi over 2.
And also up until like what number, like up until what number covers the section we already went through, like the sines and the.
Well, anything that just has sines or cosines, you can do. The secant tangent problems I'm teaching you how to do today. So,
Okay, so like number 5, I wouldn't be able to do.
yeah, and if you look down further, there's some other problems like that. So go
Okay.
through anything that's just sines and cosines you can do now. 16 you can do now, 17 you can do now.
Okay.
18, this is a fun problem. This looks like it's going to take forever, but it's not. The answer is the same in each case. They just want you to see that this can be done 3 different ways. 19 you could do now, 20 you could do now. And then after today, you'll be able to do all the secant tangent problems. 14 from last week. So homework 3, number 14, you can look at that too. Let me knock this one out first. Did I just close that? It was 9 times the integral from 0 to pi over 2 of sine squared, right? Cos squared, sorry. All right. And we're using the variable theta, so I'll use the variable theta. All right. So Damodar, we'll go back to that one after this. This guy, first of course, we pop out the 7, and I have integral 0 to pi over 2. Does anybody remember the procedure for even powers? If both the powers are even, and here the power of sine is 0, which is even, the power of cosine is 2, which is even, so here both powers of sine and cosine are even, what do we do in that instance? Who remembers?
Could you do 1 plus cosine of 2 theta? Like use that the
half angle identity. Yeah. So I'll replace cosine squared by his half angle equivalent, which is 1/2 1 plus cos 2 theta. And any time where both the power of sine and the power of cosine are even, that's what we do, right? We talked about this on Monday. If both powers are even, then the only thing you can do is beat those to death with the half angle formulas. Another problem where you'll get a lot of practice with this is number 4. Here, both powers are even, so you'll have to beat these things to death with half angle identities before you can evaluate them. But this one's actually pretty easy. I'll pop out the 1/2, so I'll have 7/2 integral 0 to pi over 2, 1 plus cos 2 theta, 2 theta. And then that is now all micro U sub stuff. The 1 doesn't require any substitution. 1 just integrates to theta. Cos 2 theta, remember all of these integrals we know quickly now, is going to be sine 2 theta over 2. And then we evaluate from 0 to pi over 2. The cos 2 theta to sine 2 theta over 2 move, that's what we call a micro U sub, right? Where you imagine substituting like z equals 2 theta. So you say, okay, dz is 2 d theta, so I'll get a 1/2 out, and then you just integrate cos z. Cos z would integrate to sine z. So you get sine 2 theta over 2. We should be able to do this step very quickly. We shouldn't have to write out the U sub anymore. And now we evaluate between bounds. So that's 7/2 times. When I plug in pi over 2, I'll get pi over 2 here. And then the sine of 2 times pi over 2 is the sine of pi. That's 0. And then when I plug in 0, these are definitely both 0. So my answer is 7 pi over 4. Not too bad. So just remember those cases, right? If one of the powers is odd, then you're going to try u sub. If both of the powers are even, then you need to just beat the thing to death with half angle identities. Here, you just need the half angle identity once and everything is hunky-dory. The other homework problem that was requested in chat came from the previous homework, homework 3, and was number, what did we correct it? 11. That's this guy. So homework 3, number 11. I want to integrate from 0 to 2 pi x times sine x times cos x dx. So this is really an integration by parts problem. And my suggestion would be to first use a trig identity on this. May not be jumping out at you, but remember that sine of 2x is 2 times the sine of x times the cos of x, which implies 1/2 sine 2x is equal to sine x cos x. So that's where I'd get started on this, is with this identity, to rewrite this piece as 1/2 sine 2x. So I'll get 1/2 integral 0 to 2 pi x times the sine of 2x dx. Just destroying my back. Let's try that until. So from here, some integration by parts is called for. This is a polynomial. Polynomial times trig function, always IBP. And what's more, my LIPET rule will tell me how to pick u. U should be the polynomial piece, because I don't have any logs, I don't have any inverses, I do have a polynomial. So I'll pick u to be my polynomial, and dv to be everything else. That's sine 2x dx. Then du is just dx, and v is the integral of sine 2x. That's negative cos 2x over 2. Again, a micro u sub taking me from here to here. So if I follow my integration by parts formula from here, that 1/2 is going to stay out front, and then I'll open a big parentheses. U times v, so that's negative x cos 2x over 2, evaluated from 0 to 2 pi, minus the integral from 0 to 2 pi of v times du, which is negative cos 2x over 2 times dx. And then close that big param at the start. So first I use the trig identity to rewrite this as sine 2x times 1/2, and I pop out the 1/2. And then I use integration by parts following my LIPET rule, where I pick u to be x and dv to be everything else. A micro u sub carries me from dv to v, and then I write down my IBP formula. My next step, I should evaluate this piece. When we plug in 0, the x will make everything here 0. When I plug in 2 pi, I'll have negative 2 pi times the cosine of 4 pi over 2. That's negative 2 pi times, what is the cosine of 4 pi?
One.
Yeah, it's 1. Is this going from 0 to 2 pi or 0 to pi? Oh, I guess, yeah, it's random. Okay. I did a version of this with someone in office hours the other day, so it varies depending on the up or down. But yeah, the cosine of 2 pi is 1, so cos 2 pi over 2 is just 1/2. And like we said, when we plug in 0, this term makes everything here 0. So this is what we get from that evaluation. And then we have to subtract this integral. Well, I've got a minus and a minus there, and I've got a 1/2 here, so I can plus out. Pop out a plus 1/2. And then I just have integral 0 to 2 pi of cos 2x dx. Uh, 0 to 2 pi, sorry. And then the integral of cos 2x is another micro u sub. That's going to be sine 2x over 2. So I'll have 1/2, and this is negative pi, plus 1/2 times sine 2x over 2, evaluated from 0 to 2 pi. That's 1/2 times negative pi plus 1/2 times, if I plug in 2 pi here, I get the sine of 4 pi, which is 0. And if I plug in 0, I get the sine of 0, which is 0. So this whole thing here is 0, which means altogether I just get negative pi over 2. Questions about this file?
No, I get it now. I just did it a different way. I did u equals x and then dv equals sine of cosine, and that made me have to do another integration by parts with sine and cosine, and then it just became all a mess. I still got the right answer, but it was a little longer than that.
So here's a suggestion, Damodar. When you get to that setup where u is x and dv is sine x cos x, try going from dv to v there with a u sub rather than with integration by parts. Sine x times cos x, both of those powers are odd. So you can integrate that a little bit more easily by letting by letting like z be sine x. Then dz would be cos x dx, and you'll get there a little bit faster. Or, and I really think this is true, you could use this identity again, right? If dv is sine x times cos x, then you can rewrite your sine x times cos x as 1/2 sine 2x. And that will make your dv to v step easier also. So if there's anything to take home from what we're doing this week, it's that trig identities can make life so much easier when you're trying to integrate. Some forms of a trig function are difficult to work with as far as calculus is concerned, and some forms are easier. For example, if I wanted to differentiate sine x times cos x, would I rather use the product rule or rewrite it as 1/2 sine 2x and use the chain rule? I think it's easier to rewrite it like this and use the chain rule. But it's a matter of taste, and it sounds like you got to the right place. Anytime you're doing integration by parts within an IBP table, like to pass from dv to v, if that on its own requires IBP, I would step back and try to see if there's a simpler way to approach the problem, because often there will be. Ooh, that's a little bit. Okay, I think there might have been one other problem requested in chat, and since today is sparse enough, we can do one more. Number 9. Oh, from the current guy. Tan to the 4 times secant to the 6. So we haven't talked about this yet, but I'll use this as my first example for the secant tangent integrals. So we're ready to start talking about the new stuff. Right, you got a power of secant times the power of tangent. The best way to get a feel for this is to start experimenting. So I said I would do this one for my first example. Was it? Damn, I closed it. Did I really close it? I don't think I did. It's just not showing up in my tab. 10 to the 4 secant 6. Okay. So when I look at this, what I see, I'm thinking U sub, right? I want to try and find some combination of trig identities and U substitution that will allow me to turn this thing into a polynomial. The only options are I can sub for tangent or I could sub for secant, right? I mean, those are the obvious options. Those are the things that I would obviously want to try. Substituting for tangent requires having an extra copy of secant squared. And substituting for secant requires having an extra copy of secant tangent. I have both of those. Right? I could set aside a copy of secant tangent. That would leave me with tan cubed times secant to the 5. So then if I substituted for secant, I would have z to the 5 times, oh, what would I do with the tan cubed? There's no nice way to rewrite tan cubed as secants. So instead, I'm going to try to substitute for tangent, which means I need to set aside 2 copies of secant. So I'll start by rewriting this as tan to the 4 times secant to the 4 times secant squared with an eye towards substituting for the tangent function. Now I still have the problem of these 4 copies of secant. But I can write them as secant squared squared. This secant squared I'm leaving alone because I want to use him when I substitute for tangent. But these guys I need to rewrite as tangents so that that substitution will be happy. So I rewrite secant squared squared, and then the inner secant squared I rewrite as tan squared plus 1 using the second Pythagorean identity. And now I'm ready to substitute for tangent. The derivative of tangent is secant squared. That's why I pulled those 2 copies of secant to the side. And now when I make this substitution, I'll have z to the 4 times z squared plus 1 squared times dz. And that is a polynomial. And remember, my goal is to get to a polynomial because I always know how to integrate those. It's not hard. Worst case scenario, you got some algebra to deal with, but it's not too bad. If I FOIL out my z squared plus 1, it's too early for me to be getting spam calls. What is this bullshit? Oh, it's my dad. I haven't heard from him in some time, but I'll have to call him back. So I'll have z to the 4 times, here when I FOIL this out, I'll have z to the 4 plus 2z squared plus 1 times dz. And that'll give me z to the 8 plus 2 times z to the 6 plus z to the 4 dz. And now I'm ready for my antiderivative. So this is z to the 9 over 9 plus 2z to the 7 over 7 plus z to the 5 over 5 plus a constant. And then finally, since it's an indefinite integral, I go back to my original variable. So that's tan to the 9x over 9 plus 2 tan to the 7x over 7 plus tan to the 5 of x over 5 plus c. So I'm going to do like we did on Monday. I'm going to go back and annotate this with the strategic steps that will apply to all integrals like this. First though, questions about the technical stuff. Why any of this came out the way it did, where that went, that sort of thing.
Why'd you make the secant squared x squared the tan instead of the other one?
Say that again?
Why'd you make the
Into
secant
this?
squared of, yeah, why'd you do that instead of doing it to the other secant squared?
Well, so this secant squared I set to the side because I want to substitute for tangent. So I need him for my differential, right? Down here.
Okay.
If I want to substitute for tangent, I need a secant squared somewhere that can be soaked up by dz. So I set him off to the side and I forget about him. And
Okay, I
the goal
understand.
is to rewrite everything else as tangents. This piece is happy, but this piece still needs work. So yeah, I grab him and I set him to the side because I know I want to try substituting for tangent. It's a good question. What other questions do we think? What other stuff's popping up in your head? While you're thinking, I'll come in here and start annotating. So the case that we're dealing with here is if the power of secant is even. Then you will set aside secant squared with the differential. Thinking of subbing z equals tan x. Sorry, this pen is just, can't seem to catch a break with these. It's a different pen than we had dying on Monday. So our first step is to set aside 2 copies of secant with the differential. Then we need to rewrite the remaining secants as tangents using the second Pythagorean identity. And that's these 2 steps here. And then you go ahead and sub for tangent. Which will yield a polynomial. And once you've got a polynomial, we're scot-free. because we know how to integrate all polynomials. So not too bad, right? If the power of secant is even, then things ain't too bad, because you can always set 2 secants off to the side, and what's left will be an even power of secant. Even powers of secant can always be rewritten as tangents. So you set 2 secants off to the side, rewrite everything else as tangents, and then substitute for tangent. That will always give you a polynomial. We know how to integrate all polynomials. You see how this is similar to the case where the power of sine is odd, or where the power of cosine is odd. You can grab one, set it to the side, rewrite everything else using Pythagorean identities, and then substitute and get a polynomial. You guys asked to see the cat yesterday, right? He's making the most adorable noises. Hey, Nova, come here, big boy. This is the kitty. This is the shy one. Yeah, you're a shy boy, aren't you? All right. So any questions on this problem? He's sweet. I'm sorry, bud. Okay. If there are no questions here, then we're going to move to the other case, the other nice case. Yeah, it's slick, right? It's not too bad. So the other nice case is if the power of tangent is odd. If the power of tangent is odd, then things are also pretty nice. If the power of tangent is odd, then I'm going to try substituting for secant. That's the basic idea. So I need to set aside a copy of secant times tangent. So I'll grab one of these tangents and one of these secants and set them over here with my differential. I'm thinking I want to substitute for secant. Here's the derivative of secant. So that's what I need to make that substitution go through. The only other thing I have to do is rewrite the remaining tangents as secants. And that, again, comes from the second Pythagorean identity. Tan squared plus 1 is secant squared, so tan squared is secant squared minus 1. So over here, you'll see if I substitute for secant, this will all be a polynomial, and then this will all get soaked up by the differential. So I'm ready for my substitution. And the result will be the integral of z squared minus 1 times z squared times dz. So we're golden. And then I'll distribute and rewrite my polynomial in standard form and integrate. So distributing, I get z to the 4 minus z squared, which means I'll have z to the 5th over 5 minus z cubed over 3 plus a constant. And that is secant to the 5 over 5 minus secant cubed over 3 plus a constant. Not bad at all. And just like I did for the other, I'll come in here and annotate. So if the power of tangent is odd, then first set aside a copy of secant x tangent x with the differential. Thinking of subbing z equals secant x. And then I rewrite the remaining powers of tangent as secants. Using the second Pythagorean identity. And then you go ahead and sub. Sub z equals secant x, which will yield a polynomial. And once you got a polynomial, you're golden. Everything's easy. You may notice that there's overlap between the two cases we discussed. It's possible that the power of tangent is odd and the power of secant is even. That's kind of like having both powers be odd in the sine cosine case. You got a choice. If the power of tangent is odd and enormous, like tangent to the 2021 times secant squared, obviously substitute for tangent. And if the power of secant is even and enormous, then you should substitute for secant. All right, provided the power of tangent is odd. So in the overlapping cases, just like when we talked about the sine and cosine integrals, substitute for the larger power. And you can play around. There's some problems in your homework that will let you play around with solving these multiple ways. Unfortunately, those two cases are not exhaustive. It's possible that the power of tangent is not odd and that the power of secant is not even. So first I'd like to take any technical questions here, any questions on the strategy, but then we're going to talk about this hard case. Questions on this problem? No, feeling good? Okay. Questions on the strategy for either of these gentler cases, where the power of tangent is odd or the power of secant is even? All right, then let's discuss the hard case. Unfortunately, there's only a few examples I can do with you here. I actually spent a little bit more than I should have wandering down a very hard example with my last class. So the hard case. What do we do if the power of tangent is even and the power of secant is odd? A few things. Cross your fingers. Find the big boy pants. And then try some IBP. Because these are hard. These tend to loop. And we've already seen one of them. Right? I showed you last week how to integrate secant cubed. The secant cubed integral is one of these because the power of secant is odd, it's 3, and the power of tangent is even there, it's 0. So let me show you one more. Here the power of tangent is even, and the power of secant is odd. So we cross our fingers, put on our big boy pants, and try some IBP. LIPET won't save you here because it's all trig, it's all t's. There are no l's, i's, p's, or e's. So when you split this and choose your u and dv, and you gotta just try some shit. My suggestion is to pick dv first. Pick dv to be something you know how to integrate. So I say, okay, I'm not gonna worry about u at the start. I'm gonna worry about dv at the start because it's all trig. LIPET doesn't help. I could take the secant times tangent. I know how to integrate that. So I'll pick that for my dv, and that means u is just tangent. Which will make du secant squared and v secant, because the antiderivative of secant tangent is secant. Now, if I plug into my IBP formula, I'll get secant times tangent minus the integral of, let's see, secant times secant squared. I'll just write that as it is. On the one hand, that is secant cubed. And I do know how to do the secant cubed integral. It requires looping. But if I'm clever, I can make this whole integral loop without having to deal with secant cubed directly. The trick is, at this step, I use a trig identity. Secant squared x is equal to 1 plus tangent squared x. So I can rewrite this as secant x tangent x minus the integral of secant x times 1 plus tan squared x dx. And then distribute. And then split up. So that'll be minus the integral of secant x dx minus the integral of, I'll write it as tan squared times secant x dx to help you see the loop. What you see is that down here, my original integral has shown back up. We've successfully looped. So I like to write the result in a single line. Integral tan squared x times secant x dx is equal to secant x tangent x minus the integral of secant x dx minus the integral of tan squared x times secant x dx. And if I add this over, I'll get 2 times the integral of tan squared x secant x dx equals secant x tangent x minus this guy is the natural log of secant x plus tangent x. And remember, he was one of the prereqs, one of the basic integrals that we needed to know before we could get started, right? Integral of secant. And at this stage, we should write our plus c because there are no more integrals on the right-hand side, and then you divide by 2 to win. You don't need to divide the c by 2 because he's an arbitrary constant. So this is where we land. It's tricky stuff. The truth is there aren't too many more integrals like this I can ask you to do. If I make this a tan to the 4 and leave this as a secant, then that integral is very hard. If I leave this as tan squared and make that a secant cubed, that's very hard. That's the one I got burned up on with my class last time. So there really aren't a whole lot more examples here that are like appropriate for our level. So I want to take a second, let you guys ask questions about this particular problem. And then part with the warning that these are fucking hard. Most of these are going to be out of reach for us. They're not impossible, but they're very, very difficult. The real skill that I want you guys to be practicing are the cases that aren't super hard, right? I want everybody to be rock stars at the U sub cases for secant tangent. Those are not bad. You can do all of those. These cases, we will encounter them from time to time, and when we do, we will deal with them as we must. But if the combined power here, right, like the combined power here is 3, 2 plus 1. If the combined power gets up to like 5, 7, these are incredibly difficult. Yeah, fair question. So my exam one always has at least one looping integral. Usually what I do is I'll have a problem there that has 2 or 3 looping integrals on it, and I say pick one and do it. It might be the damped harmonic oscillator, it might be secant cubed, it might be tan squared times secant, but it'll have at least one thing like this. Any integrals like, sorry, go ahead.
Will you put an example of like the looping, like one of the looping integrals on the study guide?
Mm-hmm. Yeah, certainly. So just for fun, let's take a look at, yeah, that was right, yeah. No, can I not type? So they're giving the natural log term as an inverse hyperbolic tangent. So this would be like the natural log of secant plus tangent. And then we've got these other terms coming out. It's very, very tricky. It's not at all easy. So I wouldn't rope you into something quite that hard, but something like just secant cubed, we know, secant times tan squared, we just did, would be fair. That's about as hard as I would ask you to do on a test. And indeed, if you flip through the textbook, you'll find no more of these than those, because they get really, really hard. There is a trick, and I'll share with you that trick in case you ever encounter something like this in the wild. So how do we handle stuff like integral of tan squared times secant cubed? What you want to do is break these down into odd powers of secant. So all of these where the power of tangent is even and the power of secant is odd, which is again the nightmare case, can always be turned into integrals of odd powers of secant using trig identities. Tan squared, remember, is secant squared minus 1. So this could be rewritten as the integral of secant to the 5th minus secant cubed. And then you would split that. And then you would run some integration by parts on this. With one run of IBP, you can turn the secant to the 5th integral into some stuff minus the secant cubed integral, or some constant times the secant cubed integral. And that will allow you to combine these. And then you can run the IBP, the looping IBP, on the remaining secant cubed stuff. But it's not pretty. It's really not pretty. Like, it's really, really hard. So I wouldn't make you do it. And you're unlikely to ever encounter it. If I'm honest, I don't know of a single place in physics or stats or anywhere that you need these integrals. Not with these large powers. There are some places in physics where you need the secant cubed integral, and we'll encounter those again and again this semester. But these higher order nightmare case integrals, you're unlikely to encounter. But if you ever do, the process is to break them down into odd powers of secant and then start chipping away at the higher odd powers of secant until you get them down to secant cubed. Once you've got all secant cubes, then you run the IBP and loop. It's hard though, it's very, very hard. I don't expect you guys to do it. I'm not gonna do it because it would take more than a whole class period to even go through one problem like this. So what I do want to do with the remaining time we have, and we may finish a little bit early today, is to introduce the material we're going to start talking about next time, which is called trig sub. This is a hard integral. So I'm moving on now. So intro to 7.3 trig sub. This, and this are all kind of tricky. They're difficult because the square roots don't play nice with the addition and subtraction going on here. This is not equal to the integral of 1 minus x. This is what I want to make clear today. This is not equal to the integral of 1 plus x. And this is not equal to the integral of x minus 1. That stuff does not work. Square roots just never do that. Right? Never ever. Square roots do not distribute over addition or subtraction. However, 1 minus sine squared theta is cos squared theta. So the square root of 1 minus sine squared is the square root of cos squared is cos theta. I'm assuming that cosine is positive, but we'll let that assumption hang out. Similarly here, 1 plus tangent squared of theta is secant squared theta. So the square root of 1 plus tan squared theta is the square root of secant squared theta is secant theta. And here, secant squared theta minus 1 is tangent squared theta. So the square root of secant squared minus 1 is the square root of tangent squared is tangent theta. So while I can't do this kind of first grade close your eyes and cross your fingers algebra, if I were to make this x sine theta, then this thing would become nice. This would become the integral of cos theta. If in this integral I was to substitute x equals tangent theta, then this integral would become the integral of secant theta. And here, if I were to substitute x equals secant theta, then I would end up with the integral of tangent theta. So what we need to learn how to do is these kind of backwards substitutions. So in 7.3, we will learn how to do the backwards. Can you be good? Substitutions. X equals sine theta. X equals tan theta. And x equals secant theta to handle not just these integrals, but any integral that has something that looks like this. Any integral that has something that looks like this or this. We call these backwards substitutions because instead of saying my new variable is equal to some combination of old variables, I'm saying my old variable is a function of the new variable, right? The original variable here was x. So I'm saying I'm going to let x be sine theta rather than saying like I'm going to let z be x squared. You see the difference? The new variable is trapped inside the function here. So these are called kind of backwards substitutions, and I would like you guys to first finish the 7.2 homework, of course, but then read section 7.3. If you don't get that done, read section 7.3. If you don't get to this by Friday, that's okay. But on Friday, I will be working a little bit with this stuff. I'll also be solving some more problems from your current homework. I want to make sure that when we get to this next week, so next week your homework will have trig, sub, and partial fractions. When we get to this next week, we can move through it somewhat quickly. The goal is to take integrals that have these gnarly square roots in them and turn them into integrals of trig functions, see? There's going to be some geometry involved, and there's going to be lots of algebra involving square roots. So you got to be comfy with that stuff. So do yourselves a favor, work hard on the current homework. Get it done, and then read section 7.3. I'll do a little bit more to help prepare you for section 7.3 on Friday, and I'll also solve a handful more problems from section 7.2 for those who are still working on that. But that's where we're going, and this is where I'm going to leave it for today. I know we're a few minutes early. Are there any last questions for me before we get out of here? So we have actually covered all we need to cover.
Hi, Professor, how are you? So I have a question not based on this directly, but I have a question more related to searching for help on the homework, for example.
Yeah.
I just moved up to Gainesville because I was back in Miami, but I moved up to Gainesville, and so I'm close to like Santa Fe. I was just wondering if their math lab is open so I can go do homework there, and if I need help, you know, they can help me over there, or is it just all virtual due to Corona?
Yes to both. So the Learning Commons is open. If you can make it physically to the library, the Learning Commons is open. They have workspaces, whiteboards, and tutors. But from what I understand, the tutors are not coming down and sitting with you. The tutoring is all still virtual to allow for appropriate social distancing. So yes to both. You can go there, and probably you can get slightly more immediate help by being there physically. But I think when it comes to interacting with the tutors, that will still have to be done through Zoom.
Got it. Thank you.
Another option, of course, if you come over here to the to the modules in our class, I do have lots of good stuff for this. So under the trig integrals stuff here, these Patrick JMT videos, these are good. Paul's online math notes is good. So here you'll see him running through some problems of the sort, excuse me, that we've been doing. And then Paul also breaks down the stuff that we've talked about in words written out. So if you prefer to read, I would look at Paul's. If you prefer to watch, I would look at Patrick. But those are really the best that we can offer aside from the office hours that I do. But I do think right now everything has to be remote because of COVID.
Awesome. Yes, thank you. I have been looking at those videos, so I'm gonna keep looking at them. So thank you.
Cool. Yeah. All right. That sounds good. Any other burning questions right now, guys?
I have a question about the homework.
Sure.
So I've been stuck on number 4 for a while.
Let's take a look at it then. Yeah.
Get all the way to like the very end, and then I get tripped up.
Okay. So we can do this. This one is tough, and I did this with my last class. So we want to integrate sine squared t times cos to the 4t dt from 0 to pi. I'm going to ignore the constant. The constant changes. The trick here, since both of these powers are even, is to use half angles. So that'll be integral 0 to pi. Sine squared is 1/2 times 1 minus cos 2t. And cos to the 4 I'll write as cos squared squared. And then that cos squared I can write as 1/2 1 plus cos 2t. And then the square on the outside is still there. So this is how we get started. Now this is a long problem. The next step is going to be to square both the 1/2 and the 1 plus cos 2t. Ooh, I left off a paren here. I need one more close paren. And bring all the constants outside. So I'll have a 1/2 here, and I'll have a 1/2 squared here is 1/4. So I'll have a 1/8 that can come outside. And then what's left will be 1 minus cos 2t times 1 plus cos 2t squared dt. Next, I will FOIL that out. So my 1 minus cos 2t still chilling. And when I FOIL 1 plus cos 2t, I'll get 1 plus 2 cos 2t plus cos squared 2t, like that. There's good news and bad news here. I'll go ahead and distribute this. And the good news is that some of these terms will be easy to deal with. The bad news is that we're going to end up with another cos squared from these two and a cos cubed from these two. So when I distribute now, I'll have 1 plus 2 cos 2t plus cos squared 2t minus, now cos 2t times 1 is cos 2t, minus cos 2t times 2 cos 2t is minus 2 cos squared 2t, and minus cos 2t times cos squared 2t is minus cos cubed 2t. And then I can combine some like terms, this and this and this and this. So I'll have 1, and then cos 2t minus cos plus 1 cos 2t, combining this with this. And then also I can combine this with this. So I'll have minus cos squared 2t, and then minus cos cubed 2t dt. This guy needs more half angle. This guy is now an odd power, so I'm going to break him off because he doesn't follow the same pattern as the other guys. The modified half angle looks like this. Cos squared of 2t is 1/2 1 plus cos of 4t. Remember, whatever's here is always half of what's here. So if I want to break this down, normally it's cos squared 2 theta equals 1/2 1 plus cos 2 theta. Just plug in theta equals 2t. So I have 1 plus cos 2t minus 1/2 times 1 plus cos 4t. And then I'm going to break off the integral of cos cubed because he gets his own treatment. Because this is an odd power, here I'm actually going to use u sub. I can distribute this 1/2. And then in this guy, oh, sorry, I wrote 0 to 3. That's 0 to pi. Close, but not quite. 0 to pi. I'm going to treat this as cos times cos squared. Because when I see the odd power of cosine, I think, ooh, I should try substituting for sine. Which means I set aside a copy of the cosine and then rewrite whatever's left as sines. So here I'll use the Pythagorean identity. Here I'll combine my like terms and just have micro u subs. This one is now easy. This piece is pretty much done. This 1 and this minus 1/2 can be combined. And I'll get 1/8 integral 0 to pi 1/2 plus cos 2t minus 1/2 cos 4t. And believe it or not, this integral is going to be 0. There's a couple ways you could see it. You could argue geometrically if you know what the graph of cos cubed 2t looks like. That's what I would do. But if you don't see that, then the normal way to proceed here would be using the first Pythagorean identity on that and getting ready to make a substitution, z equals sine 2t. dz would then be cos 2t times 2 dt. And you also need to change your bounds. When t is equal to 0, z is the sine of 2 times 0, which is 0. And when t is equal to pi, z would be the sine of 2 pi, which is also 0. So your new integral is actually going to run from 0 to 0. Like I promised back here, this whole thing is 0. So everything is going to come from this guy. But we can go ahead and see how he wraps up. My antiderivative here from this first piece is 1/2 t plus micro u sub sine 2t over 2 minus micro u sub. This would be sine 4t over 4, but there's already a 1/2 here, so that's sine 4t over 8, evaluated from 0 to pi, minus here I'd get the integral from 0 to 0 of 1 minus z squared times 1/2 dz, the 1/2 coming from the differential. But the integral from 0 to 0 of anything is 0. So this piece is definitely 0. Because the integral from a to a of anything is always 0 if your upper and lower bounds are the same. And this piece I can evaluate. So when you plug in pi, you'll get 1/2 pi, or pi over 2. This piece would be the sine of 2 pi, that's 0. This piece would be the sine of 4 pi, that's 0. And then when you plug in 0, this is 0, this is 0, this is 0. So that's everything right there.
Why are the bounds of the second integral 0 and 0?
So remember how we calculate the new bounds. When we go make a substitution, we plug the old bounds, which were 0 and pi, into the substitution. So if I plug in 0 for t here, I'll get z is the sine of 2 times 0, which is the sine of 0, which is 0. So when t is equal to 0, z is equal to 0. So my new lower bound is 0, just like my old lower bound. When I go to try to find my new upper bound, I plug my old upper bound into the substitution. So I'm plugging t equals pi in here. So when t is equal to pi, z is equal to the sine of 2 pi, which is also 0. So it's the same procedure we always go through to change our bounds. You plug the old bounds into the substitution. It's just that when you do that, the new bounds both come out to 0. Another way to see that, and again, I don't necessarily expect you guys to be able to picture this in your head right away. Not cos squared, cos cubed. Oh, that's right, Desmos doesn't like that. So here's cos 2t. If we look from 0 to pi, you see that he spends just as much time below the x-axis as he does above the x-axis. And the cubed version will do the same. They just look a little different. So from 0 to pi, you've got the same amount of stuff upstairs as you have downstairs. So you can make a symmetry argument to say that the integral of this from 0 to pi is 0. But I think the more natural thing from the Calc 2 perspective is to just go ahead and do the problem. Go ahead and make the substitution. And as long as you change your bounds, you'll see right away that this integral has to be 0. This is one of the many, many reasons why I require you guys to change your bounds when you make a substitution. And maybe now's a good time to remind you that we're getting close to the exam. Anytime you make a substitution in a definite integral, you must change the bounds. And this is a good example of a problem where doing so saves you a lot of time. You don't have to then integrate and evaluate this piece. You see right away, oop, my new lower bound is 0, my new upper bound is 0, so this integral gotta be 0. Is that making sense?
I think so.
Okay. So I do have to go ahead and sign out now. We are out of class time. I hope that you guys are enjoying these problems, putting time into them. Integrals of trig functions are hugely important. If this was a Calc 2 honors class, or if we had more time, I would love to talk to you about Fourier series because they're probably the most important little bit of applied math in the world. And it all revolves around integrals of trig functions. But for now, we're just trying to develop these skills. So keep working on the homework. And if you happen to finish the homework before our class on Friday, please read section 7.3 in the textbook. Reading this at least sometime before next Monday is necessary. Reading it before Friday would be nice, but you must read this before next Monday. If you have the time to read it before Friday, that would be good. It will help you understand the little introduction lecture I'm going to do on that. Alrighty? Okay, if you do want to talk more problems, I have an office hour this afternoon, normal time. You can find the link in Canvas on our main homepage there. Otherwise, I will see you guys on Friday. Have a lovely rest of your day.